We're probably familiar with this equation. This is an algebraic equation of a line at y equals 2. Now what if you replace y with a derivative? This is what we call a differential equation, an equation that has derivatives. Intuitively, a differential equation describes the rate of change of a quantity with respect to another quantity. A differential equation can be an ordinary differential equation, or ODE, which incorporates ordinary derivatives like these. The first equation is a first-order ordinary differential equation, since it has a first derivative. The second and third equations are second-order ordinary differential equations, since the highest derivative in the equations is the second derivative. The third equation is the same as the second equation. It just uses a different notation, which is y prime instead of dy over dx. A differential equation can also be a partial differential equation, or PDE, which incorporates partial derivatives. In this video, we'll focus on ODEs. PDEs require more advanced techniques. Let's go back to dy over dx equals 2. We aim to solve for y. But it turns out, y equals 2x is a solution. Just plug in 2x to dy over dx, and we'll see that the result is valid. But also, 2x plus 1, 2x plus 2, 2x minus 1, 2x plus pi are also solutions, since plugging in the derivative of a constant is 0, and the operation still yields to 2. We can say that the general solution to dy over dx equals 2 is y equals 2x plus c, where c is some constant. We can impose an initial value condition. Let's say y equals 1 when x equals 0. Now what's the solution? Well, we get the general solution first, then solve for the constant c given initial conditions, which yields c equals 1. Hence, the particular solution to the initial value problem is y equals 2x plus 1. In general, a differential equation has a general solution, which is a family of solutions that satisfy the equation. There can also be a particular solution when you impose initial value conditions. Why do we study differential equations? Well, it's often used to model physical phenomena. It is used in physics, engineering, chemistry, biology, and even economics. Some examples include rectilinear motion, population growth and decay, simple harmonic motion, electrical circuits, Newton's law of cooling, etc. In the next chapter, I discuss how we solve these differential equations. Let's first consider the first-order differential equation. If we have an ODE of this form, this is a separable differential equation. Basically, separate them so that one side is g of y dy and the other is f of x dx. Then integrate both of them and see where we can go further. Example: consider the growth and decay problem earlier. We just separate the variables and integrate them. Take the exponential of both sides to obtain p. Since e to the c is just some constant, the solution can be written as this. This is the equation for the exponential growth and decay. Now this next part requires you to know a little bit of multivariable calculus, specifically partial derivatives. If we have an ODE of this form, yes, we can write it that way, where m and n are functions of x and y, then this is exact if there exists a scalar potential function such that its partial derivative with respect to x is equal to m, and its partial derivative with respect to y is equal to n. Going back to the first equation, the condition of exactness tells us that if the partial derivative of m with respect to y and the partial derivative of n with respect to x are equal, then the equation is exact. And then the solution to the ODE is just the potential function equals the integration constant. Example, consider this ODE. Taking partial derivatives, indeed, it is exact. To find the potential function, we define these relations. Then maybe we choose the first equation and integrate with respect to x. You'll see that we added g of y, an arbitrary function of y. To find g of y, we again differentiate the expression with respect to y, then we equate it to x plus 2y. Then we solve for g of y through integration with respect to y. Thus, the solution can be written as this. Moving on, if we have an ODE of this form, or this form, we can try to multiply the entire expression by something called the integrating factor. How do we find mu of x? From there, the left-hand side of the equation can be matched directly to the derivative of mu of x y by the product rule. Then, we match mu prime of x y equals mu of x p of x y. We can drop the y. This is a separable ODE. I'll leave it to you to do the rest of the steps, but by solving that ODE, we obtain the integrating factor to be this form. We're not yet done, because we will now derive the general formula for the solution. Remember the right-hand side, mu of x q of x? We can also equate it to the derivative of mu of x y. Integrate both sides with respect to x. And we finally obtain the general form of the solution. Just take note of the integration constant. Example, consider this linear ODE. We find the integrating factor first. Then we use the formula we derived earlier to solve the ODE. As for how we obtain the answer to the integral, the method used is integration by parts. In solving ODEs, you may want to recall integration methods, especially in Calc 2. Now sticking to linear equations, what if the highest derivative is second order, third order, fourth order, fifth order? Well, we need to establish some theoretical framework for solving higher order linear ODEs. Consider this general form of a higher order linear ODE. Considering this is an initial value problem, an nth order differential equation will require the following n initial conditions. Now, the existence and uniqueness theorem states that if the functions p0, p sub 1 up to p sub n minus 1 are all continuous in some open interval I containing x0, then there exists a unique solution on I. The next part, and expect a general theme of that in this section, will incorporate some topics in linear algebra. Maybe I'll try to make a video on this soon. How do we solve this ODE? Well, we're not there yet. But what we can do is to think of a solution that could work. Consider the general form of the ODE, but this time q of x equals 0, making it homogeneous. Then if you have y sub 1, y sub 2 up to y sub n as solutions to these homogeneous ODE, then the linear combination of these solutions is also a solution to the ODE, where c sub 1, c sub 2 up to c sub n are constants. But is this the general solution? We're not so sure, because we could keep adding more solutions. What we want to find out is if y is linearly independent. Here's the basic definition of the linear independence of solutions. But we have a systematic way of finding this out, and that is through the use of a matrix determinant called the Wronskian. If the Wronskian is non-zero, then the solutions are linearly independent, and they form a fundamental set of solutions. And we have a general solution to the homogeneous ODE. Examples. Consider these two sets of solutions. Are these two sets linearly independent? Well, let's do some determinant calculations. We can see that both sets are indeed linearly independent, as the Wronskian does not equal 0. Let's now solve linear homogeneous ODEs with constant coefficients. We'll get back to the non-homogeneous case later. Let's assume a solution, y equals e to the rx. We plug it to the equation. Then, if we cancel out e to the rx, that leaves us with a characteristic equation. We just do algebra and solve for the roots of the equation. The nature of the roots of the characteristic equation will determine the general solution. We have three cases. The first case is if we have real distinct roots. The second case is if we have real repeated roots. And the third case is if we have complex distinct roots of form r equals a plus or minus bi. Where the heck did sine and cosine come from? Well, it might not be very nice to express the solution in imaginary numbers, but the magical Euler's formula saves the day. I'll leave it up to you to derive the whole thing. Now remember that we have proven that exponential sine and cosine functions are linearly independent, so the solutions make perfect sense. Example. Let's try to solve this ODE. Immediately, we treat it as a characteristic equation, then solve for its roots. You may use rational root theorem, synthetic division, and quadratic formula, etc. As you can see, we have a real and a complex distinct root. The general solution is then just the sum of the solutions. For r equals -1, we have c sub 1 e to the negative x, and for r equals 2 plus or minus 3i, where a equals 2 and b equals 3, we have c sub 2 e to the 2x cosine of 3x, plus c sub 3 e to the 2x sine of 3x. Let's go back to the non-homogeneous case. The general solution is actually still the solution in the homogeneous case. We'll label it as y sub c, plus something called the particular solution, labeled y sub b. How do we get y sub b? This is where the method of undetermined coefficients come in. I think it's best to explain this concept with an example right away. Let's solve this ODE. We solve for y sub c first. That is, assume the ODE is homogeneous. We use the characteristic equation method. For y sub b, let's assume that it equals e to the 2x. But then we have an undetermined coefficient called a, in which we need to find a. To find a, we compute the first and second derivatives of y sub b. Then, we substitute all of that into the original ODE. Finally, we solve for a. Thus, we now have a particular solution. As mentioned, the solution to the ODE is y sub c plus y sub b. In general, we can use the method of undetermined coefficients if the function is an exponential function, polynomial, sine, or cosine. We then form a guess of the form of a particular solution, plug into the differential equation, simplify, and set the coefficients equal to solve for the constants. Another method for non-homogeneous case is the variation of parameters. This method will make use of the Wronskian and can be used for more classes of functions. Let's use this method to solve the same ODE in the undetermined coefficients method. We have already solved the homogeneous solution. Now in this method, we assume the particular solution is equal to the sum of the two linearly independent solutions, y sub 1 and y sub 2, which are obtained from y sub c, then multiplied by some unknown function, u sub 1 and u sub 2. In this case, y sub 1 equals e to the x, and y sub 2 equals e to the negative x. How do we find u sub 1 and u sub 2? The derivation is long, but here is the general formula for order 2, where w is the Wronskian and r of x is e to the 2x in the problem. We already calculated the Wronskian determinant earlier in this video. Then we compute for u sub 1 and u sub 2. Lastly, plug in and simplify. We find out that indeed the solution we obtained here is the same as the one we obtained from the method of undetermined coefficients. There is another powerful way of solving ODEs, and that is the Laplace transform. Defined as this improper integral, it converts a function to a different type of function that depends on a different variable. In this case, the Laplace transform converts a function from x space to s space. Conversely, an inverse Laplace transform converts a function from the s space back to the x space. Example, let us find the Laplace transform of e to the ax where a is some constant. Let's just do the integral. Notice the condition where s is greater than a, since the improper integral converges only with that condition. Computing improper integrals takes time, so a table of Laplace transforms is usually used for easier memorization. At this point, I'm just gonna show the table from my notes. Enjoy my handwriting. Now, if you look closely, it turns out derivatives and integrals can also be transformed using the Laplace transform. This is what makes Laplace transform a powerful tool for solving ODEs. Basically, we can now convert a differential equation to an algebraic equation, solve that algebraic equation, and then convert it back using the inverse Laplace transform. Example, let's solve this ODE that describes simple harmonic motion. Before that, let's use a different notation. The dot over x just indicates the time derivative at order 2. Let's impose some initial conditions. Take the Laplace transform of both sides and obtain capital X of s. Use the inverse Laplace transform to obtain x of t. We then recognize from the table of Laplace transforms that these correspond to the sine and cosine functions, respectively. After treating x0 and v0 over omega as some constants, we have our solution. If you are not convinced by this answer, you can always plug in the solution to the ODE and check if it matches, or just Wolfram Alpha if you're too lazy. It's fine, sometimes I get lazy too. At this point, we have covered a lot in ODEs, but there are more topics I haven't discussed yet, such as substitution methods in homogeneous first-order ODEs, graphical representations, series solutions, systems of ODEs, nonlinear ODEs, numerical methods, and so on. There is a lot to talk about in this math discipline. This video is getting a little bit long. I have presented simple examples, but ordinary differential equations can get pretty freaking tedious to solve. Enjoy the brief compilation of me solving ODEs. We haven't even talked about partial differential equations yet, which is a whole other beast of its own. The existence and smoothness of Navier-Stokes equations, which are PDEs, remains one of the unsolved Millennium Prize problems, with a reward of $1 million for anyone who can solve it. By the way, this is an overview of finding analytical solutions to ODEs. If you want a more application-focused and geometric interpretation of ODEs, I recommend you watch 3 Blue 1 Brown's Tourist Guide to ODEs. If you are currently taking a differential equations course, my advice is to review your algebra and calculus, and to be frank, just practice. Maybe the wasted time of yours doom scrolling could be dedicated to solving differential equations instead. I do hope this video at least gives you an idea of what to expect in an elementary differential equations class. Definitely subscribe for more videos like this. Thank you.